Hello calculus fans, and welcome to section 3.3 where we are going to look at the derivatives of trig functions. And before we get started with this, we need to do a little proof here. So we need to prove this. So we're going to develop these derivatives. In order to do that, we need to prove that the limit as theta approaches 0 of sine of theta over theta equals 1. And theta will be in radians. So the radians are important. In order for this proof to work, we need to be measuring in radians, which is what we typically will do in calculus. And when we develop these trig functions, there's a couple things that we're going to need, and this is one of them. We need this in the development of the trig functions. To come up with the derivatives, we're going to need this statement. So this is what we're going to prove. But before we do that, we need to review some things. So let's just review a little bit. Starting with maybe a circle. So do a little review here. Some terms that we're going to need to know. So let's say we've got this circle, and we have this angle coming out. We'll call this angle theta. And then this distance here along the circle, that arc length, we're going to call S. And then this distance here from the center of the circle out to the circle, of course, is the radius. And you have probably seen before in the trig classes that theta is equal to S over our radians. Right? That's how we define radian measure. By this angle right here, it's just the arc length divided by the radius. That's radians. You may even remember from a trig class, if you open this angle enough so that S equals R, so if S equals R, we have 1 radian. This is roughly 57.3 degrees. So what we need out of here, though, is we need to talk about the area of this sector. So the sector of the circle, this little region right in here, this little pie shape. We need to come up with the area for that. So let's look at this. The area of a sector. So again, the sector is this little pie shape here. Well, we can look at something. We could say, well, the area of this thing, this area of this shaded region here, that area, that would compare to the area of the entire circle, which is pi r squared, right? The area of a circle is pi r squared. That would compare in the same way that theta would compare to 2 pi, right? So 2 pi, where's that from? Well, if I open this angle so it goes all the way around the circle, if we were using degrees, we'd say there are 360 degrees in a circle. But when we use radians, we say there are 2 pi radians in a circle. So the shaded area compares to the area of the entire circle in the same way that theta compares to the total angle measurement in radians in the entire circle. And then we can use this to solve for the area of a sector. So since this is a proportion, a fraction equal to a fraction, we know that in that case we can take the cross products and they'll also be equal to each other. So what we could say is the area times 2 pi is equal to pi r squared times theta. Here we can see there's a pi on each side of the equation, so we could cancel those out, like we could divide each side by pi. And then from here, we could, to get area by itself, we could divide each side by 2. So we would get the area is equal to, instead of dividing by 2, I'm going to pull that the half out and get area equals 1/2 r squared theta. So the area of a sector is 1/2 r squared theta. Let's just make a note of that. We'll kind of set it aside, and we're going to have to use that in a few minutes. Okay, so let's go back up to this proof that we have to show. And remember that theta will be in radians. And I'm going to draw a sketch here. And I'm going to show the proof that is typically shown here. It's a geometric proof. Now, once we have something called L'Hopital's rule, we'll be able to prove this really quickly, like very fast. But we don't have that yet. So with the tools we've got now, we're going to have to rely on trigonometry and some algebra to make this proof happen. So let me start off with a picture. All right, so this is what we've got. We've got not the greatest picture, but use your imagination and pretend this is a quarter of a circle. So there's this circle here, and let's say this is a unit circle. So this dimension here is 1. This is 1 unit. This is 1 unit here, and then so this is actually also 1 unit here. Okay, we've got this angle we'll call theta, and theta is in the first quadrant, and theta is definitely less than 90 degrees. And let's see, so this being 1, being a unit circle, this will come here, so this point A would actually be the point 1, 0. And then what we've got is this line that comes out here, and it goes up to here, and then this is a perpendicular line that hits that, and then this of course is straight up also. So that this little part here would be a sector of a circle, and this is a straight line here from P to A. Okay, so when you look at this, if you think of the sine of theta, so sine of theta, if I use this angle here, or this triangle OQP, sine of theta is going to be opposite over hypotenuse, opposite of hypotenuse. So if I write that down up here, I get the sine of theta equals the opposite. Now in this case, the opposite would be the length of PQ. So I'm going to put absolute value to mean like the magnitude of PQ over 1, which just means basically it's the magnitude of PQ. Right, so I can even write that right here. So this is going to be sine of theta. The length of PQ is sine of theta, right? Because theta is opposite over hypotenuse, and the hypotenuse is just 1. So this length is sine theta. Okay, likewise, if we look at cosine of theta, so cosine of theta is adjacent over hypotenuse. So the adjacent is whatever the length of this segment OQ is. So that is going to be the length of OQ over 1, which is just the length of OQ, which means that I could just say that this is cosine theta, right? So cosine theta is going to be this length over 1, and so it's just basically this length. So that's cosine theta. And then one more, let's look at tangent theta. Now for this one, we're going to use this bigger triangle here, OTA, and I'm doing it purposely because I'm picking ones where there's going to be a length of 1 for one of these. So you can see, like, if I use this big triangle and I use tangent, I have the opposite over the adjacent. The adjacent side now has a length of 1, right? Because this point A is 1, 0. Remember, it's a unit circle. So this has a length of 1. So we could say that tangent theta is going to be the length of TA over 1, which is just the length of TA, which means that this length here is tangent theta. Okay, so we've got our picture set up. We'll start with this one statement. We're going to start by saying, let angle theta be between 0 and pi over 2. So we want it to be an acute angle, bigger than 0 but less than 90 degrees, right? Less than pi over 2 radians. Remember, what we're doing here, this whole thing is just to prove this statement. We're going to need this statement later. So we're going to prove this statement right now. All right, so we start with this, and then I'm going to make a statement here and see if you agree. So I'm going to say this. I'm going to say that the area of triangle OAP is less than the area of sector OAP, which in turn is less than the area of triangle OAT. So let's look at what this says. So the area, triangle OAP, so OAP, remember this is that straight line up here. that's going to be less than the area of sector OAP, because OAP sector has this curved area. So this little area here in the sector, right? This little sliver that's in the sector that's not in the triangle, so the sector would definitely be bigger. And then sector OAP is definitely smaller than the area of triangle OAT, which is the bigger triangle. Okay, so let's look at those areas and see what they are. So area of a triangle we know is 1/2 base times height, right? So 1/2 base times height, in this case would be 1/2. Now the base is going to be 1. The base of this triangle OAP, the base here is 1, right? For the length from OA. 1/2, so I'm basically using the formula for a triangle, 1/2 base times height, right? So 1/2 base times height. Now the height of that triangle is sine of theta, right? So triangle OAP, the height of it is sine of theta, right? And that is less than the area of sector OAP. And here's where that formula from above came for the area of a sector. Remember, area of a sector, I'll write that here, 1/2 r squared theta. So in this case, it's going to be 1/2. Now the radius squared is just 1 squared, so it's just 1, and then theta. Then we're saying that this is less than the area of triangle OAT. Well, that's going to be 1/2. The base is still 1, right? Because this is triangle OAT, so the base is still 1. And then the height here is going to be tangent theta. Okay, so we've got this. And so basically what we've got is 1/2 sine of theta is less than 1/2 theta, which is less than 1/2 tangent theta. Okay, now I know you don't really know why we're doing this yet. It's not really an easy one to figure out, but if you just follow through here, and you'll see that we're gonna head to where we need to be. Okay, just gotta trust me on this one. Okay, I know how much you love proofs, so here's a proof for you. So far we are to this step here, and now we need to think about what we're doing. So this angle theta. Okay, so think about what we're at. We can say this: since sine of theta is greater than 0 for the values that we are working with for theta between 0 and pi over 2, right? So that's where we're at. Let theta be between 0 and pi over 2. And just think of the graph, the sine graph here. So if you look at the sine graph between, so let's say this is pi, and here's sine, it goes up like this, right? Here's pi over 2. So on this interval between 0 and pi over 2, sine is definitely going to be positive, right? There's no negative values there. Okay, so because of that, if we were to divide this compound inequality by, say, sine of theta, we could do that. We know it's positive, and we wouldn't have to worry about reversing the direction of the inequalities, right? So remember in the good old days in algebra class, you'd have something like 3 minus 3x is less than 12, and you're solving this inequality, and you're like, okay, I'm going to divide by -3. And you're super excited. You're going to get to the answer. And then these cancel, and you get x, but remember we divided by a negative, so we have to reverse the direction, right? So it's sort of like that. So what we want to do is clean this up a little. So I'm going to divide everything by, let's just get rid of the 1/2s too. You guys, does everybody agree I could just divide this whole thing by 1/2 and nothing would change? Right, 1/2 is positive, so let's just do that. Let's just divide everything by 1/2 and we'll get this spot. Okay, now what I'm going to do, since this is true, since sine of theta is greater than 0 for these values that we are interested in, right, for these values here, since that's true, I could divide this compound inequality by sine of theta, and I wouldn't have to worry about reversing the direction of the sign. These signs would stay exactly the same, right? So I can just divide everything by sine of theta. Divide by sine of theta, sine of theta, sine of theta. And then what we would get would be 1 is less than theta divided by the sine of theta, which is less than tangent of theta divided by sine of theta. Okay, now let's just look at this over here, this tangent theta over sine of theta. Let's see what that really is. Well, tangent is just sine of theta over cosine theta, then dividing that by sine of theta, or sine of theta over 1. Well, that's the same as taking sine of theta over cosine theta, and instead of dividing, multiplying by the reciprocal, which would be 1 over sine of theta. Then we can see that would cancel, and that would give us 1 over cosine of theta. So really what this compound inequality says is this. Okay, and then what we're going to do, we can take the reciprocal of everything as long as we reverse the direction here. Okay, so I can just take the reciprocal of all these things if I reverse the direction. So if I take the reciprocal of 1, I get 1. Take the reciprocal here, of course, I get sine of theta over theta. And over here I get cosine of theta over 1, or just cosine of theta. And then whenever you have a compound inequality, if you remember in the past and you've seen them, you always have them pointing the other direction because you want the smallest number on the left, biggest number on the right. So I'm just going to reverse these. So I'm just going to write it the other way. I'm going to write cosine theta is less than sine of theta over theta, which is in turn less than 1. And we're okay. It's still, like when I compare sine of theta to cosine, it opens at sine of theta, right? Still opens at sine of theta. And same with this. 1 is greater than this. 1 is greater than that. Okay, so we're over here. All right, and then, do you remember how much you loved the sandwich theorem? We get to use that again. So what we can do here, we've got this inequality. We're interested in this, right? We were looking for the limit of this function as theta approaches 0. All right, so let's consider this. We could say this. We know that the limit as theta approaches 0 of cosine of theta. Well, cosine's a continuous function, so to take that limit, I can just plug in 0, right? Cosine of 0 is 1. Also, we know the limit as theta approaches 0 of 1. Well, that's just the limit of a constant. That's 1. So look what we've done. We've taken the limit of this as theta approaches 0, we got 1. Took the limit of this as theta approaches 0, and we get 1. And this is squished between them, right? So then we could say, therefore, by the squeeze theorem or the sandwich theorem, however you want to, whichever term you prefer, by the squeeze theorem, we can say that the limit as theta approaches 0 of sine of theta over theta equals 1. And that's what we needed. All right, I hope that proof didn't have the same effect on you as it did on these three knuckleheads. These tend to get very sleepy during proofs. But hopefully you guys were very energized by the proof, right? You guys still there? Okay, that was the worst of it. Okay, unless you like proofs, then that was the best of it. But now we need to move on. So we do have one more proof, but it's a little bit shorter. It's actually a lot shorter. Next proof goes like this. And again, you'll see why we need these as soon as we get done with this proof. We need to now prove that the limit as theta approaches 0 of cosine theta minus 1 over theta equals 0. Now this one we can do more in a more familiar way. Okay, we're going to do something sort of like what we've seen before. So if you remember in section 2.3, we'd have proofs sort of like this where when I plug in 0, I get cosine of 0, which is 1, minus 1, which is 0 over 0, right? So I get a 0 over 0. And then we had some techniques we would go through, and this one is going to look a little bit like that. Okay, so here is the proof. It's gonna sound familiar. It's not exactly what we've done, but if we take the limit as theta approaches 0 of cosine theta minus 1 over theta, and we get 0 over 0, but we're going to multiply by this 1, and it's going to feel sort of like the conjugate. It's the same sort of idea. And it'll just happen to work for us in this case. So when we do this, we're going to get the limit as theta approaches 0, and the pair that's like a conjugate pair will FOIL that, and that will give us cosine squared theta. Outside and inside will cancel, so we'll get minus 1. On the bottom, we'll have theta times cosine theta plus 1. And then let's look at that cosine squared theta minus 1. It looks so familiar. So we do know this, right? We do know that sine squared theta plus cosine squared theta equals 1. So we're going to have something really close to that, but not quite that. So we know that sine squared theta equals 1 minus cosine squared theta. That's not quite what we've got. But what if I multiplied each of these, each side of this equation by a negative? Then I would get minus sine squared theta equals negative 1 plus cosine squared theta, or in other words, cosine squared theta minus 1, which is what we've got. So really, this thing could be replaced with negative sine squared theta. I know it's a little strange with the negative, but it will work for us here. So let me rewrite this. So let's say then this is equal to the limit as theta approaches 0. And I'm going to write negative sine squared theta over theta times cosine theta plus 1. And then because this negative sine squared theta is the same as negative 1 times sine squared theta, I'm going to just rearrange this a little bit. I'm going to put... actually, I don't know why that equals. That little dot is there. Okay, so we can go, this is equal to, I'm going to move that negative out front, so I'm going to have negative 1 times the limit as theta approaches 0. And then let me write something, you guys tell me if this is okay or if I'm just making something up here. Sine of theta over cosine theta plus 1. Okay, what do you think about this? Limit as theta approaches 0 of this. I move the negative 1 out here. And I'm going to basically split this into two parts. I'm going to put one of these signs over the theta, the other one over cosine theta plus 1. Because really, if you think about it, we could multiply these together. Sine times sine is sine squared, and then this times that would get us back here. Okay, so if we split up like this, we've already just shown what this is, right? So the limit as theta approaches 0 of sine of theta over theta is equal to 1. So we have negative 1 times 1, and then we can plug this in. So let's just figure out what that one is. So that's going to be negative 1 times 1 times, now if I plug 0 in here, I get sine of 0, which is 0, and then this is cosine of 0, which is 1 plus 1. But so I get basically 0 over 2, but that's just 0. So the whole thing is 0. Okay, so we needed to show that, and that is what we've shown. So now we are ready to go. Okay, we've got the two proofs we needed to come up with the derivatives of all the trig functions. So let's try our first one. If f of x is sine of x, what is f prime of x? Well, what we could do is use our limit definition of a derivative. We get the limit as h approaches 0 of f of x plus h minus f of x all over h. And so in this case, we get the limit as h approaches 0 of sine of x plus h minus sine of x all over h. And at this point, to make this work, as you can see, if we start plugging in zeros, we're just going to get 0 over 0, right? Because we'll get the sine of x minus the sine of x, which is 0 over 0. So to get out of this, we're going to use a formula you've probably seen occasionally. Not a lot, but you've probably seen this occasionally. This formula, it's a sum and difference formula. So the sine of a plus or minus b is equal to the sine of a times the cosine of b, and then plus or minus cosine of a times the sine of b. Okay, so we're going to use the minus one, of course. So we're just going to use it to expand this, because once we do that, then we're going to have a way to get at this. All right, so then this would be equal to the limit as h approaches 0. So sine of x plus h is going to look like sine of x cosine h plus cosine x sine h minus sine of x. And let's see, we'll put this all over h. Okay, so algebraically, I'm going to tweak this a little bit. I'm just going to move this negative sine of x over here. So I'm going to move this over here and rewrite it. Okay, so we're going to write, this is equal to the limit as h approaches 0, sine of x cosine h minus sine of x plus cosine of x times sine of h all over h. Okay, and then we'll do a little bit of algebra. And I'm basically going to look at these first two terms, and I'm going to factor out a sine of x. All right, so I'm going to factor out sine of x there. And we'll get cosine of h minus 1. And then over here we have plus cosine of x times sine of h all over h. Okay, then what we need to do is we're going to split this up. Okay, now just going to use a little algebra here. Limit as h approaches 0. So what I'm going to do is put these two over their own h. Okay, I'm going to put them over their own h. So I could write this as sine of x times cosine h minus 1 over h plus cosine x times sine of h all over h. This would be the limit of this big thing. Okay, I don't know why the screen keeps moving on us like that. Okay, so now we are really close. So this, if I just tweak this a little bit more, I'm going to write it like this. Sine of x times cosine h minus 1 over h plus cosine of x times sine of h all over h. Right, so just verify algebraically this is okay, right? Because this would be like sine of x over 1, and then I could multiply a fraction straight across. Same with this one, cosine of x over 1. But now we can take the limit. Okay, the limit as h approaches 0. We've just shown that this, the limit of this as h approaches 0 is 0. And this one, the limit as h approaches 0 of this is 1. So we can take the limit. At this time I take the limit. We get sine of x times 0 plus cosine of x times 1. So we get cosine of x. So we have just shown that the derivative of sine of x is cosine of x. All right, so here we go. The 6 trig functions, derivatives. We found one, the derivative of sine of x is cosine of x. Now here's the nice thing about this is we really only need to find 2 from scratch. We need to find the derivative of sine of x, which we did, the derivative of cosine of x, which I believe is a homework problem, but it can be found just very similar to the way we found this. But once we have these two, all 4 of these can be found in much easier ways, because isn't it true you can write all 4 of these trig derivatives, or these trig functions, in terms of sines and cosines? So for these 4, if you just rewrite these in terms of sines and cosines, then you can just use the product rule and quotient rule once you have these 2 established. Okay, now remember that these are only valid when x is measured in radians. those proofs that we did only work with radians. So it turns out when you use derivatives with angle measurements in degrees, degrees are sort of an arbitrary made up thing, whereas a radian is part of a circle. So when you use degrees, you have these multipliers that you have to use all the time. So remember, these are only valid when using radians. So when you're in your calculator or when you're using your calculator in calculus class, you almost always want radians. Okay, so I'm just going to tell you these, okay? So the derivative of sine is cosine. The derivative of cosine turns out to be negative sine of x. So the derivative of tangent is secant squared of x. The derivative of cotangent is similar, but it is going to be negative cosecant squared of x. Okay, and then secant and cosecant are kind of similar. When you take the derivative of secant, it comes back, secant x times tangent x. And similarly, for cosecant, it also comes back, but with a negative cosecant x times cotangent of x. So some things to notice that'll make this easier, because we have to know these 6. We have to know them really well to do well in Calc 1 and beyond. They'll come up all the time in your calculus classes or classes that use calculus. So the way to remember it is notice all the co-functions, cosine, cosecant, cotangent, they all have negative derivatives. All negative, right? All negative. Typically, this is the easiest one to remember. Sine is cosine. And if you know that, then you pretty much know this one too. Derivative of cosine is sine, but it's a negative because it's a co-function. The way that I remember this, tangent being associated with secant squared, is I always think of that trig identity. There's that trig identity that says tangent squared theta plus 1 equals secant squared theta. So I sort of have these two functions linked anyway. So the derivative of tangent is secant squared. And then if the derivative of tangent is secant squared, then it's kind of easy to remember what cotangent would be with a cosecant, and it's a cofunction, so it's negative. And there's also this similar Pythagorean identity for cotangent, right? Cotangent squared theta plus 1 is cosecant squared. So there's that too. So that's how I remember these. And then secant and cosecant, they just come back. All right, take the derivative of secant, it reappears with tangent. Once again, I always kind of associate secant with tangent. And with cosecant, same sort of situation. First, it's a cofunction, so it's negative. Derivative of cosecant is negative cosecant times cotangent. And the easiest way to remember these, if we were in a face-to-face class, I would probably 4 or 5 times during the next couple of class periods, I would put these on the board and have you try to remember them and pull them out of your memory without looking. And if you make yourself do that a few times, you will get it. You really will. It's not that bad if you do it a few times. And just think of like little memory hooks you can remember. Sine goes with cosine. Cosine goes with sine, but it's a negative. All the cofunctions are negative. You just want to like write down these 6 trig functions and then practice filling in their derivatives, because we really have to know them. All right, now that you have these, I know what you're thinking. You're probably thinking, I cannot wait to try these out. I know, I'm ready. So here is an example problem. Let's say f of x equals x times the sine of x. And of course, when you look at a function, the first thing you think is, I wonder what the derivative is, right? I know exactly what you're thinking. Like a mind reader. So f prime of x equals, okay, so look at this one though. You have to be careful. Product rule, right? Product rule. So with that in mind, why don't you take a minute and see what you come up with. Remember, don't wait for me. Press pause on the video, try it out, and then check back. Okay, so hopefully you checked it out, you tried it yourself. And with the product rule, remember there's a couple ways to do the product rule. There's the traditional way, which is typically taught like first term times the derivative of the second term plus the second term times the derivative of the first term. There's that way. Or there's a way that I think is a little easier where you just write them down. You write it down twice with a plus. And you take turns of the derivatives. So you say like, okay, derivative of this one first and the derivative of this one. Either way, it doesn't matter. As you talked about earlier, you get the same thing either way. So the derivative of x is just 1, of course. So you get sine of x plus x times. The derivative of sine is cosine. Okay, so not too bad, right? What about this? What if you have this example? What if you have f of x equals 5 times the sine of x? Okay, here's a question. Do you need the product rule here? Do you remember what you talked about? Do you need the product rule here? You don't need it, right? You can use it, but you'll just kind of waste your time because you'll have something like this where the derivative of 5 is just 0, so it wipes that out. Remember that this is a multiplier. This number that's being multiplied just goes along for the ride. So you don't need the product rule if you don't have two functions or two variables. Here we've got a variable here and a variable here. We need the product rule. They're being multiplied. Here we just have a constant times this function with a variable. So the 5 goes along for the ride, and f prime of x is just going to be 5 times cosine of x. Okay, so the point is if you just have a constant here, you don't need a product rule. You can use it, but you just be sort of wasting this step here. Okay, but I know what you're thinking. Sure would like to see one with a tangent and a secant. Okay. All right, you came to the right place. I got one for you. How about y equals tangent x minus 1 over secant x? All right, everybody's favorite, the quotient rule. Do you remember that jingle? I know you kind of like that jingle, right? Low, d high, minus high, d low, all over the square of the bottom we go. All right, take your new knowledge and that snazzy jingle and give this one a try and then check back. Okay, hopefully you are trying these and then checking back. So we have got y prime equals. All right, I'm going to just say the quotient rule jingle as I write them. So low, remember it always starts low. Low, d high meaning derivative of high. Low d high minus high, d low, derivative of low, right? That's a secant. All over the square of the bottom we go. Remember with trig functions, when we write this, what this really means is secant of x squared, right? So it really means this. It's just we typically write it this way, okay? Just kind of keep that in mind. All right, so then we've got derivatives to take. We need to take the derivative of this one and the derivative of this one. So let's see, that gives us secant of x times derivative tangent is secant squared x. The derivative of 1 is just 0, so that's just gone. Minus tangent x minus 1. The derivative of secant x is secant x times tangent x. Okay, one thing to keep in mind when we first start, we have to be careful with this. Okay, sometimes I'll see students write something like this. Secant tangent x, okay? That's not what we want. What this is saying is that tangent x is the argument to the secant function, right? So we need, these trig functions need arguments. It's secant of x, tangent of x, right? These are the inputs or the arguments. So you don't want to skip that, right? These each have their own inputs or their own arguments. Okay, all over secant squared of x. All right, now of course we want to clean up the numerator. All right, we want to clean up the numerator. So we can multiply this. And this one, there's two terms here, so we're going to have to distribute this through, right? Now you may notice you can cancel a secant first, but let's not. I think most people maybe wouldn't notice that. So yeah, let's just distribute this through, and then we'll worry about the secant at the end. Okay, so if I multiply here, I get secant cubed x minus, now this is one term, right? And it's going to come through here and here. I also have to be careful about this negative. Okay, so I'm going to keep the negative here. And then just to make it clear, I'll distribute first. Okay, so I'm going to get secant tangent times tangent, which is going to be secant x times tangent squared x. And then minus secant x tangent x. I'll put the red there. Right, so this is from secant tangent times tangent, which is secant x tangent squared x. And then we have secant x tangent x times 1, which gives us this. And then this is all over secant squared x. So this gives us secant cubed x. I'm going to distribute the negative through and get secant x times tangent squared x plus secant x times tangent x all over secant squared x. And now I know you guys would never leave it like this because there are 1, 2, 3, 4 terms, and what do they all have in common? Secant, right? So we can cancel a secant out of everything. It'll be secant squared, that will be gone, that will be gone, and this will be secant to the first power. And that's one that I had mentioned. You may have done that ahead of time. Okay, so some of you would have canceled this ahead of time. Minus tangent squared x plus tangent x all over secant x. And then you might even notice one more thing. Pythagorean identity. Tangent squared x plus 1 equals secant squared x. We've got this right here, right? So what if I subtract tangent squared x from each side here? Then we get 1 equals secant squared x minus tangent squared x. So that this is just equal to 1. So this gives us basically tangent x plus 1 over secant x. So that's a good one. That one just kind of kept on going, right? A lot of algebra, a lot of trig, and even some calculus. So the homework problems in this section will be combining everything so far. So we'll have the product rule and the quotient rule, but now we'll have these trig functions scattered in there. Okay, but one thing to remember though that I'd mentioned, I'll just write down number 24. So then the 9th edition, number 24 says, show that the derivative of secant x equals secant x times tangent x. Okay, so this one's going to be much easier. Once we have sine and cosines derivatives established, we can just rewrite these in terms of sine and cosine. So what I need to do really is much easier than doing this from scratch. Secant is the same as 1 over cosine of x, right? So I can just take the derivative of this with the product rule. Or sorry, with the quotient rule, right? So with the quotient rule, I can say, okay, low d high, low derivative of high minus high derivative of low. All over the square at the bottom we go. Okay, so we figure this out. Well, the derivative of 1 is 0. It's just a constant, so that whole thing is gone, right? Derivative of 1 is 0. So we just get negative 1 times the derivative of cosine, which is negative sine, right? All over the square of cosine squared x. So this is really just sine of x over cosine squared x. And if I wanted to do something different here, couldn't I just go 1 over cosine x times sine of x over cosine x? Isn't that really These are the same, right? So you go straight across, you get sine over cosine squared. And 1 over cosine, that's secant x, and sine over cosine is tangent x. Okay, so we've shown that. So when you have to show these, as I mentioned before, the only ones that work are sine and cosine. We've already done sine. The rest of the other 4 trig functions we can write in terms of sines and cosines and just do something similar to this. So I think you should be all set. So go ahead and try the homework on 3.3. And of course, if you have any questions, let me know, and I will talk to you soon.